Hi everyone. Today I'm gonna present our work on semi-supervised 3D medical segmentation from 2D natural images pre-trained model. All the code and trained model weights can be found on the GitHub link on the bottom left corner. Large-scale 2D natural image datasets have led to powerful vision models. But in medical imaging, especially 3D segmentation, the major bottleneck is still the scarcity of label data. So the central question of this work is, how can we utilize pre-trained 2D vision models to improve 3D medical segmentation when only a few manual labels are available? To achieve this, we propose M and N, where M stands for medical images and N stands for natural images. Our M and N progressively distills knowledge from a pre-trained 2D model into a 3D medical segmentation network trained from scratch. It is model agnostic, meaning that our proposed method can be integrated with different models and architectures. We will show more details later in the result session. Also, it is aimed for using only a few labeled medical images for training. And for me, most importantly, we are aiming for a simple approach. Many of the existing semi-supervised segmentation approaches are based on complicated or complex design. And we prove that a conceptually simple method can be a strong baseline. So we have the pre-trained 2D model and the randomly initialized 3D model. We start with training and fine-tuning them with a small set of labeled images. The 2D pre-trained model can be fine-tuned by different strategies, such as NORA or whole network training. And we will show you the more detailed comparisons in the result session later. The next step is the iterative code training. Each training batch mixes real and pseudo-labeled data. On odd-numbered epochs, the frozen 2D model generates pseudo-labels to train the 3D model. While on even-numbered epochs, it reverses. The frozen 3D model generates pseudo-labels to fine-tune the 2D model. This is done back and forth. Due to the significant imbalance between the size of the labeled and unlabeled set, uniform data sampling during the code training may undermine the training stability and final performance. Even with conventional strategies like oversampling, a fixed sampling strategy may not be optimal. Therefore, we propose a simple trick called learning rate guided sampling. We are using a weight decay cosine scheduler to adjust the learning rate during training. At early stages, when the model's predictions are still unstable and inaccurate, relying heavily on their generated pseudomasks may be suboptimal. Therefore, the proportion of pseudo-labeled data in each training batch should be fewer. As training progresses and the predictions become more stable and accurate, unlabeled images in a batch, which are used as pseudo-labels, should increase accordingly to maximize the utilization of unlabeled data. So later in the result sessions, we will show you more details about the ablation experiments. We evaluated on the MLMI LA cavity and pancreas CT datasets using different numbers of labeled data settings, which ensures that our proposed M and N works on different modalities and scenarios. To test the model agnostic nature of our approach, we tested on a pre-trained setformer, which is a transformer-based model, and a pre-trained ResUnet, which is a convolutional neural network. Similarly, for a 3D network, we tested on 3D-UNet and SwingUNet-R to make sure that our approach works on both CNN-based as well as transformer-based networks. Here are the results on the pancreas CT dataset. We first look at training a 3D unit using just 6 label data. It achieves a die score of around 60%. Using the same amount of label data to train a 2D subformer from scratch, a significant drop of performance is observed, which may partially suggest that a 3D network, rather than a 2D network, may be more suitable for 3D medical segmentation tasks. Using the same 2D subformer, but pre-trained with natural images first, and fine-tuned with 6 label medical data, saw a significant improvement, which may suggest that 2D natural images pre-training may be helpful for 3D medical segmentation. And our proposed MNN pushes this limit from die scores of 68% to 81%, using the same amount of labeled medical training images together with unlabeled data. And qualitatively, you can also see an obvious improvement brought by our proposed MNN. Compared to other existing semi-supervised segmentation methods, MNN outperforms all of them. On the MLI-LA dataset, using 4 and 8 label training data, similar results were obtained. Our proposed MNN outperforms all other methods under different settings. And finally, we conducted detailed ablation experiments. First, by replacing our proposed iterative co-training with fixed pseudo-label training and the LRG sampling with uniform sampling. A drop of performance is observed, which validates the value of these 2 proposed components. Secondly, we tested on using different 2D and 3D models and network architectures. While some variations of performance are observed, they consistently outperform the existing state-of-the-art methods ADMT. This validates the model-agnostic nature of our proposed MNN. Last but not least, we tried different strategies to fine-tune the 2D natural images pre-trained model, and both whole network training and the more recent NORA performed similarly well, and again outperformed the existing state-of-the-art ADMT. So we can conclude with all these experiments that MNN outperforms 13 semi-supervised segmentation approaches across datasets, modalities, and different no-label settings. Our ablation experiments also prove that MNN is model agnostic. This flexibility ensures that it can potentially adapt to future models and architectures to achieve even better performance. Personally, I think the biggest contribution of this work is to provide a conceptually simple yet state-of-the-art baseline for future benchmarking. And all the codes and trained model weights are publicly available. Thank you very much.